n number of time intervals. That's why it is indicate n. N is the number of sampling pulses. Next one is unit rectangular pulses. Next one is unit rectangular pulses. A unit rectangular pulse is a sequence of the form v of n equal to 1 if a less than or equal to n less than b, 0 otherwise. P means pulse rectangular sequences. Here we are observing pulse rectangular sequences. That means the pulses are forming like a rectangular shape. The pulses are forming like a rectangular shape. That's why these are called rectangular pulses. That's why these are called rectangular pulses. So we are observing total pulses a minus b, a minus 3, a minus 2, a minus 1, a plus 1, a plus 2, a plus 3, b minus 1, b plus 1, b plus 2, b plus. That means the sampling pulses are quantized into equal intervals that will form like a square. That's why that will like form a rectangular shape. That's why these are called a unit rectangular pulses. Next one is unit impulse sequences. The unit impulse sequences is also known as the delta sequence. The unit impulse sequence is also known as delta sequence, and it is denoted as delta. Here delta is represented or defined as delta of n equal to 1 if n equal to 0 and 0 otherwise. The first order differentials of u is delta, that is delta of n equal to u of n minus 1. The running sum of delta is u, that is u of n equal to summation of k equal to minus infinity n delta of k. A plot of delta is below. Here we are observing delta of n equal to total pulses or total unit volume is divided into the equal intervals like 0, 1, 2, 3, 0, minus 1, minus 2, minus 3. That means unit volume is represents the equivalence of the total signal. And next one is properties of unit impulse sequences. For any sequence x and any integer constant n naught, the following identity holds: x of n delta of n minus n naught is equal to x of n naught delta of n minus n naught. For any sequence x and any integer constant n naught, the following identity holds: summation of n equal to minus infinity to infinity x of n delta of n minus n naught, where x is equal to x of n naught. Trivially, the sequence delta is also even. Next topic is discrete time systems, DT. DT. Okay, discrete time systems. How to define discrete time systems? A system with input x and output y can be described the following equation. A system, the input x and output y, the input x and output y can be described the following equations. Can be described the following equation. Y equal to h of x. Y equal to h of x, where h denotes an operator or transformation. H denotes an operator or transformation. Note that operator h maps a function. Okay, next one is DT systems. Okay, DT systems, a system with x input and y output, it can be described y equal to h of x, where h is denotes an operator or translation. Note that the operator h maps a function to a function, not a number to number. It is like a function to function. Alternatively, we can express the above relationship using the notation x tends to y with respect to function of h. X tends to y with respect to function of h. If clear from the context, the operator h is often omitted, yield the abbreviation notation x tends to y. Here, note that symbol arrow and equal to have very different meanings. The symbol arrow should be read as produces. Read as produces. And next one is block diagram representations of discrete time system. Block diagram representation of discrete time system. In discrete time system is expressed the function h of x. The system function is h, and input side we are applying x input, and output side we are getting y output. So that's why it function or discrete time system receives x inputs and transmits y outputs. So that's why often a system defined the operator h and having x input and output y is represented in the following block diagram is shown below. Why we are using discrete system devices? Why we are using systems? By using switching systems. By using switching systems. We can convert the signals. Is in the form of digital. We can convert the signals is in the form of digital. So discrete pulses are more convenient to convert the signals from one form to another form, like discrete to digital. So that's why, and these are more useful to convert the signals from one form to another form. Next one is introduction of systems. First one is series, second one is parallel. Two basic ways in which systems can be interconnected are shown below. Two basic ways in which systems can be interconnected are shown below. X of n is input side we are applying, and x of n, y of n is output waveform. X of n is input waveform and y of n is output waveform. Here we are using two systems in series form. Here we are using two systems in series form, system 1 H1 and system H2. We are also arranging system 1 and system 2 in parallel. At the situation we are adding and we are using adder on to mixing the circuits, at the same time convert the signal conversions from one place to another place, or sender to receiver or receiver to sender. So that's why we are using adder. Why we are using adder? To adding system 1 and system 2 signals, and then after it will execute or propagates the data information from one place to another place, from one place to another place. A series or cascade connection ties the output of one system to the input of the other. The overall series connected system is described the equation y equal to h2 into h1 of x, and a parallel connection and a parallel connection and a parallel connection ties the inputs of both systems together, sums their outputs. The overall parallel connected system is described h1 of x plus h2 of x. Why it is like right as h1 plus h2? Why? Because when we are observing parallel diagram, we are using adder. That's why we are adding system number 1 and system number 2. So when we are calculating the output function of parallel series, that is represents y equal to system 1 plus system 2, system 1 and system 2, system 1 and system. So that's why we are using parallel and serial data communication systems. Why we are using this type of systems? So by using parallel and series, they are more convenient to convert the signals from one form to another form. Next one is properties of discrete time systems, DT. Properties of discrete time systems, DT. Next one is properties of discrete systems. Memory and causality. Okay, memory and causality, there are few points are there. First one is a system with input x and output y is said to be have a memory if for any integers n0 and y of n0 depends on x of n and x of n for some n0 equal to n0. n not equal to n naught. A system, second point, a system that does not have memory is said to be memoryless. A system which is having memory element, that is a memory device. A system does not have any memory devices, that is called memoryless devices. Why? Because internally they are not using memory devices. That's why these type of devices are known as memoryless devices. Although simple, a memoryless system is not very flexible since its current output value cannot rely on past or future values of input. Why? Because, for example, if any input, for example, we are using memory devices. For example, we are using memory devices. It will store a lot of information. But if any system is not using any devices or any memoryless devices, any memory devices, that means they are not storing any device. So that's why these are called memoryless devices, and they are cannot useful for further communications. Why? Because it is not using any memory device or memory uh, section. So that means the data will be propagated from sender to receiver only, and we can't review, and we can't see the past and previous data. Why? Because we are not arranging memory device. A system with input x and output y is said to be casual if for every integer n naught and y of n naught does not depends on x of n, some n greater than n naught. If the independent variables n represents the time, a system must be a casual order to be physically realizable. Okay, non-sequence systems can sometimes be useful in practice. And however, since independent variables need not always represent time. For example, in some time situations, the independent variable might present position. Might present situations. Next one is invertibility. Invertibility means inverse. For example, a system function is represents h, and the invertibility function is represents h inverse. That's why these are called invertibility functions. Invertibility functions means they are performing reverse operation of general systems. So that's why in this, a system where the input and output are equal, a system is said to be invertible If it is has a corresponding inverse system. Equivalently, a system is invertible if it is input x can always be uniquely determined from its output y. Note that the invertibility of a system, which involves mapping between functions, and the invertibility of a function, which involves mapping between numbers, and fundamentally different things. An invertible system will always produce distinct outputs from any two distinct inputs. To show that a system is invertible, we supply find the inverse system. To show how that a system is not invertible, we find distinct inputs that result in identical outputs that result in identical output. In practical term, immutable systems are nice in sense that their effect can be undone. So these are the different topics. Next class we are discussing more topics. Thank you.